Live streaming is
on. Hello, everybody, and welcome to WiMLDS Hyderabad's 7th Meetup. And thank you all for joining us and who had registered for this event. This event is on computer vision. It's a sort of introductory session. And as we all know, computer vision has become hugely popular these days due to its numerous applications. And today with us, we have Tatiana, who's a Ph.D. in physics, but she decided to change her careers during her 2 maternity leaves. So again, she's also a Kaggle mom. She's pretty active there. She's a Kaggle competition expert. And currently, she's working as a machine learning R&D scientist at the Infant Center at Cork Maternity Hospital in Ireland. She has a wide variety of experience in computer vision and deep learning, and she'll be sharing with us some of these experiences with regards to computer vision. Hi, Tanya, and over to you.
Hello. So hello, everybody. Today, my talk is rather introductory about Python for computer vision. As many of you have heard, computer vision now is a very popular field. And as many of you are interested in it, you definitely have heard about it. So today I will give rather quite an introductory talk about this field, and we will show some how to build some basic classifier using the Python libraries and PyTorch in particular. And then I will give you some real life examples and will explain why not everything is so easy in computer vision. So what is computer vision? In computer vision, we want to make computers see. You can see that the Wally has some cameras, and we have those cameras everywhere. Nowadays, everybody has a smartphone. We have baby monitors, security cameras, infrared cameras, LiDARs, and so on. So every one of us produce a lot of information, captures pictures, captures videos, and all that information that is generated every second on our planet, we now want to use to make computers see. And what do we mean by seeing is we really mean understanding. So when you look at this picture, you can straight away see the girl, you can see the cat, you also can see the face of the girl, and you can see how happy she is. And the cat, I'm not so sure. So basically, we want to make computers to gain this high level of understanding from images and videos, just like we do. And in fact, this is not an easy task. Usually, when we talk about vision, we actually must say that vision begins with eyes, but it truly takes place in the brain, here in the visual cortex. And so by seeing, we really mean understanding, and making computers see is actually to gain this high level understanding from images and videos is not that easy, because Mother Nature took 540 million years to make us see. And a lot of this time went into the development of the visual cortex, not actually the eyes themselves. So as this computer vision task is quite complicated, it can be broken down into simpler tasks. So the typical computer vision tasks are classification, when you classify what is that on the picture. So here you can see a person and a person. Identification, who exactly is that? So it's Uma Thurman and John Travolta. Object detection, you locate the objects where they are. Then segmentation, where exactly is that? You get the masks of the objects. Action recognition, what are they doing? And as well as pose estimating. And finally, you have scene understanding, what is happening on the image, and it's a man and a woman dancing. So why those tasks are important and why we're talking today about them? Actually, we are visuals by nature, and therefore it's not surprised that computer vision applications are so spread, and you have so many cases for applying computer vision in practice. So, for example, computer vision can be used in biomedical applications to classify cancer histograms and also select individual cells. It is used in self-driving cars to detect and select cars and road signs and traffic signs, identify pedestrians, and so on. It is also used in security for identification and action recognition and see what is happening. It can be used in art for style transfer and also to create animations for the movies like WALL-E. And it can also be used in the medical diagnostics for pneumonia detection, to classify anomaly, and so on. So basically, computer vision has a lot of applications. This is not all of that. It is also used in retail, in agriculture, and so on. So now we will consider one example of those applications. If you have seen the movie called WALL-E, you may recall that it was robot Eva who came on Earth with a mission. And she had a mission to find a plant. So now we will consider that problem, how we actually can teach Eva to find a plant, how we can program her. And basically, we are dealing with the classification problem. Eva needs to identify where is a plant and where is not a plant. So how we are going to teach Eva to do that? We are going to use supervised training. We are going to teach Eva just like we teach our children. When we teach our children, what is that? We show them the object and we name it. We say, look, this is a grass, and this is a grass, and this is a can, and this is a ball, and this is a bicycle. That's how we teach our children. So we are going to do the same with Eva. We are going to provide her examples of different objects with labels and name them. So this is called supervised training. But first, we need to get a lot of data. Basically, by the age of 3, our children are able to identify different objects around them. They can name bicycles and ball and can and so on. So the same with the computer vision program. You have to show the computer vision program a lot of examples similar to what humans see in their lifespan by the age of 3. And to get a lot of these examples, it's a different task. So thankfully now we have a huge ImageNet library, which has a lot of images, like 15 million images with 22,000 of categories of usual objects around us from everyday life. And nowadays you can get to the website, imagenet.org, and you can download, let's say, you type a tree and you can download the images of the trees, different, and so on. And there is a full ImageNet library with a lot of images, and there is a smaller ImageNet library, smaller version for benchmarking. So that's where you can get the data. Now let's look at an image from the computer point of view. From a computer point of view, an image, it's actually a three-dimensional array of numbers in the red, green, and blue channels. So all those numbers give those pixels on an image. So essentially, you are sending to a computer a 3-channel array of numbers. This is your input. And you also send into computer a label. You need to say, computer, this is a tree. And then it goes to some machine learning algorithm, and it gives you some output, what it thinks it is. It gives you an output as a form of probability, whether it's a tree or a cat or a tower, and so on. So, and the particular family of algorithms that deal with this kind of problems very well is called neural networks. What are the neural networks? The neural networks were inspired by our biological neural networks that we have in the brain. In the brain, we have different neurons, and they collect a signal from the neighboring neurons, transform it, and send it further to the other neurons. So the same idea was utilized for creating artificial neural networks. The artificial neuron collects inputs from the other neurons, summarizes them, applies some nonlinear function, and sends it further to the other neurons. You can see this course on Computer Science 231 from Stanford. It's for free, and it gives great information about computer vision in general and neural networks. So typically, neural networks nowadays have millions of nodes and millions of parameters and billions of connections. And of course, we have much more in our biological brain. So how the supervised training is happening? We send our image to a neural networks, and it propagates through the nodes and give you an output. And then we compare this output with a true label. So to compare that output with a true label, we introduce a loss function. The loss function is bigger when the mismatch between your output and the label is bigger. So what you really want to do is to minimize the loss function. So you want to tune the parameters of your neural network the way that the output will correspond to the true label for many images. And this reminds me a bit of a guitar tuner. So basically, when you play the guitar, you take a guitar, and in the beginning it is untuned. So you can turn on your guitar tuner, and you pull the string, and it tells you, this is not correct. We need to move it a bit. So you pull the string a bit, like you change parameters in your neural network in the way to minimize this mismatch. And you check again, and you tune again, and you tune again, and you tune again, unless your guitar is tuned. So this is basic understanding how it works. And if you want a better understanding, there is a course on Coursera called deeplearning.ai, where it explains very well the concept of the gradient descent algorithm and how it works, and how those parameters of the neural network are tuned. It gives you all the math about it. This is just to give you the idea of the main principle, how it works. So then when we tuned all our neural network parameters, it's time for the inference and validation. What does it mean? It means that we send to the program the unknown image, the one that it did not see yet. And we see what it will predict. And hopefully it will predict what it should, that this is a cat. So in the validation, you send images without labels, but you know that labels. And you use that labels to validate your image. And now, when you are happy with the model, this is when the true exciting phase happens. It's called test. You send your EVA to the wild. You send your program to the test time when you don't know what's going to happen, what it's going to see, and you don't have images and labels about the test in advance. So this is a true test of your model. And such models are nowadays created mainly in Python. Python became a language of machine learning nowadays. And why is that? There is a great reason for that. Python has a lot of convenient frameworks which already implemented a lot of useful functions and algorithms. And all you need to do is just to construct your programs like a Lego from those building blocks. So Python has a lot of deep learning frameworks like PyTorch, TensorFlow, Keras, and it also has a lot of other frameworks that help in computer vision tasks like OpenCV, argumentations, torch vision, NumPy, sklearn, and so on. So now we will consider how to build some easy-peasy pipeline using those Python libraries. So we will not go for ImageNet because it's a very big data set. There is a smaller data set called CFAR, when it has only 10 classes and small size of the images. It's quite easy to get the data, so I will use PyTorch in this example. There is also TensorFlow with Keras and other libraries. PyTorch became hugely popular in the research. If you look at the papers with code and all the recent SOTA in the field, you will see a lot of code in PyTorch. It's very flexible and easy to use, and people like to make experiments with it. So to get data in PyTorch for the CFAR data set is as simple as just importing one line. So then you get your train set and your test set, and you define your data loaders. The data loaders send your images with labels to your program. So you define train data loaders for train set and test data loader for the test set. Okay, you got the data. Now you often want to pre-process data. Two convenient libraries for that are OpenCV and argumentations. In OpenCV, you open an image and you can, for instance, resize an image and do some simple operations. And argumentations allow you to amend your image. Because in the wild, you can have different versions of the same image, you want your program to be ready for that. So, for instance, in the test time, you can see a parrot differently from different angle and different size, and it can be blurred and it has different color and so on. So you take an image and you produce different versions of it. So when the computer programs see different kind of parrots, it's ready for that. And it also helps computer program to avoid overfitting, to remembering your particular parrot, because every time you send your data to the model, they are augmented, so they're changed. A convenient library for that I personally use is Argumentations, where you can define different transformations to your image and get them all together. Like here, you have a crop and a flip and hue saturation. And then you also need to normalize your images because neural networks are working better when your images are normalized around 0. So it's also doing that for you just in one line. Now you need to set up the model. Nowadays, you don't need to write your neural networks yourself. Pretty much many of them are already available. For instance, you can import from Torch Vision models library a lot of models that are already pre-trained on ImageNet. So pre-trained equals true means that this model already has weights that has been pre-trained on ImageNet. It's very convenient, and usually the pre-trained models converge faster and better, but not for every task, but usually they do. So you can import some easy model, and now you need to choose that loss function and optimize it, how you are going to optimize it. It's also in PyTorch is done in 2 lines. So for this classification problem, the cross-entropy loss is a popular loss for this kind of problem. And quite popular optimizers now is a family of Adam. It's Redam, Adam, AdamW, those optimizers. So, and you set up your learning rate, initial learning rate. You can also change your learning rate when you train your model and declare the schedulers, but we will not do in this rather simple example. And then you train your model. So you basically loop over data many times. Each time you go through all the data, you call it epoch. Then you get the data from the train data loader. It gives you your images and your labels. You get your output, and you calculate your loss, which is mismatch between your outputs and your labels. And then when you have your loss, you propagate it backwards using backpropagation. So what it means that here you tune the parameters of your neural network in the way to minimize your loss. And it's also a good idea to attach your loss and save it somewhere. You can use different loggers. You can write your own logger for that. I use Neptune nowadays and very happy with that. So, but you better save your training history, of course, to see how it is going. And then you can validate your model and run the inference. So here you disable gradients and you load data from the test loader this time. You have images and labels as well. You calculate outputs, but now you see what is the most probable prediction. So you want to make sure that for the cat, it predicts cat. So how you choose it, you choose the prediction of the model with the highest probability, for example. And then you introduce some metric. For the well-balanced data sets, you can use accuracy, for instance, and you see how many of the predictions are actually correct on your validation. And that's how you monitor the training of your model. You do that after every epoch, basically, and you see when your model on validation, how it behaves. When it on validation stops training, it can still continue training on train, but it means that the model gets overfitting. The good course on that is deeplearning.ai, as I just said. So it gives all that information in details. This is a PyTorch example for you to start with, but I encourage you to do that course on Coursera because it's really very good course on that. So, however, this was a toy example, yes, so we've done it like in 5 minutes, but in real world, everything is not quite like that. The real world is hard. And why is that? Because in real world, we have very different examples. For instance, you need to classify a cat, but your cat can be hiding somewhere and your computer program needs to deal with that. You also can have different poses of the cat, like you didn't expect that, and your program probably didn't expect that. Even your cat maybe didn't expect that, but you need to still identify a cat. Also, you have interclass variations, so the objects of the same class can be very different. Illumination variations, and you can just have confusing images, like a bicycle on a car in a self-driving. So all those things happens in life, and that's when your program may be not doing that well. But ideally, you want it to do well, and there are ways to deal with that as well. So this is basically the problem that we encounter, that it's everything works on a train and on validation, but then when you use your project, your program in production, you may have some unexpected things, and often it means you need to collect more data or generate more data of those special cases and a bit to train your model so it can deal with that. So, however, there are still some things that models cannot do. So this is from the blog of Andrei Karpathy from 2012. And back in 2012, it was a problem with mirrors and 3D structures of the scene that we could not get. Now we actually can do it. So we can identify mirrors and we can reconstruct 3D from 2D. But there are still some things that the computer programs cannot do. They're not human. So here you can see that Barack Obama is stepping on the scale, and you understand the humor of the situation, that the scale will show slightly bigger result, and the person on the scale looks confused. So you can see the intentions and you can see the humor of situation. You can understand what's in people's mind. And this is something that we didn't even start to think about in terms of computer vision and in terms of the scene understanding. So far, we can identify objects and identify people and do understand 3D already and mirrors. However, there is still much more to do in the future. So we now went to the age of 3 years old in terms of progressing those neural networks, but we are very far from the age of 14. So those are the references I used in my presentation. So the computer vision class that I like from Stanford is here, Computer Science 231. And I also like MIT classes on that. And those are the links to the libraries that I used here. And I think we're ready for the questions.
Thank you, Tanya. Very good presentation, very nicely explained. And yes, we have quite a number of questions. So one of the most common ones that is asked today is, which is better for computer vision, TensorFlow or PyTorch, and what are your personal experiences with them?
Well, it depends. I would say like that. In research, PyTorch. For the production, TensorFlow. So I like, TensorFlow 2.1 now available, and TensorFlow from version 2 became very similar to PyTorch. You can easily define your data sets and things like that were good for PyTorch. They took in TensorFlow version 2. And maybe I'll change my mind, but for now, for the research, when you look for state-of-the-art models, if you go to papers with code, most of them will be on PyTorch. So when you want to quickly try ideas and implement prototype and do your research, I would go for PyTorch. However, for production, TensorFlow, is easier to convert for using on different devices like tablets. In reality, you want your program to be used and interact with users. So the serving of the model is very important. And for this particular serving tasks, I think TensorFlow is better.
Okay. So there's another question in continuation. So if there's a person who has sufficient knowledge of machine learning, but is absolutely new to deep learning and computer vision, which is a good resource to learn PyTorch?
I wouldn't start learning PyTorch. I will start with learning fundamentals of computer vision and deep learning. And I myself found a very good course, a very easy to understand course, which is called deeplearning.ai. It's on Coursera by Andrew NG. It's very easy course in terms that you don't need to have high math or PhD in physics to understand it. And yet it gives all necessary information. A bit more advanced course is Stanford Computer Class course, but that course maybe requires you to have quite a good solid background in terms of education. So after that, I would just try to implement simple programs in PyTorch. There are plenty of tutorials online now. Abhishek started his blog, YouTube blog, for instance, where he gives some live examples. He's Kaggle Grandmaster in all.
Yeah, he's just mentioned in the comment that a nice presentation. He's also watching it.
So his YouTube channel is quite good because he has great experience himself, and I liked his PyTorch tutorials, and I liked his approach to do things well. But first, you need to do deep learning course on Coursera, please, because if you just will do fit predict, you just will not understand how it works. You need to understand fundamentals first, and then do that fit predict with PyTorch and try to implement some models and try to train some models first. Okay. In my opinion.
Yeah, it makes a lot of sense. Machine learning is not just fit predict. You should also know the fundamentals and basics. So there's another question that we have. It says that when we compare programming languages, Python is very slow. So if there's a chance of replacing Python with any other language, I don't know, so it doesn't fit to computer vision, but do you really find that Python is very slow when working in computer vision? And if you could possibly replace it with another language?
So there are different modes that you consider. You can consider your research and your training, and you can consider inference and on your test time. So for the inference, people often convert programs, and they convert in C++. Basically, C++ is a language which is faster for the inference. For the training, it's not that much issue because I'd say it takes time anyway. So, and you basically, I think there was some benchmark showing the time for training using different libraries, like using PyTorch or PyTorch Lightning, using TensorFlow. There was that benchmark. I can't find it now. And the real benchmark, basically, when people use the same data set and compare the time, for instance, how quickly they can train ImageNet and so on. So I think the winner is now still TensorFlow, and then you have PyTorch, like basically on the position of 6. But the difference in time is not that great, and it's more attributed to certain tricks. So how people define their learning rate, scheduler, and what optimizers they use, how they change your learning rate, how they start. So all those things for training seem to be quite effective in terms of speeding up the training. So there is no need to write your training code in C++. But once you train the model and you want to have efficient, fast inference, yes, you usually transform your weights, because you have a trained model. Basically, it's a graph with the weights, right? This is just numbers that you can transform from one language to another. So you transform it to an X, and then you transform it, and C++ will be, I guess, the language which is the fastest for the inference.
Okay. Yeah. So another question is, nice introduction. Is there a way we could know features detected by a model after training, such as in predicting bicycle, model may use wheel as a feature. So is it possible if we could know what were the features which were detected by the model in predicting something?
So basically, there was a nice paper that visualizes layer by layer, actually feature maps of your neural network, and you indeed can see, you can visualize your, you have the convolutional filters, they extract some features from your initial image on different layers, and you can see, for instance, on early layers, they extract some textures, and then they start to extract some shapes, and on the further layers, you extract, let's say, the owl or the eyes of the owl, and so on. So there is a paper about that. Indeed, you can visualize it, and it has been done. Again, I don't have a reference at hand. I can send all those references after the talk. I need to Google with them. So yes, you can.
Okay. Yeah, sure. I can just put it in the comments after that, so people can just go through them.
I can send all those links yeah, later.
Yeah, you can share the links afterwards also. Okay, so there's another question. How do we do hyperparameterization? Is there any tool for that?
Yes, you can do a simple grid search. You can use HyperOpt, Bayesian optimization. There are plenty of tools for that, actually. But often you just start with common sense and you twist it a bit, using grid search, basically. I must say that that parameters tuning often don't contribute that much as, let's say, better data. Sorry. And sorry.
So that happens when you're a mother also and you're a machine learning researcher also.
Oh, it's so embarrassing. I'd say the most important for your accuracy, if you look at the Kaggle competitions, the one who often will win is those who used best external data, if they are allowed, of course. So basically, having a bigger and better data set and better augmentations contribute more than all that hyperparameter twisting, in my own opinion. So I will just start with finding parameters that work, and maybe twist it a bit, but not spend too much time on it, because it's more important to get relevant data for the task.
Okay, so that's another question by the same person, Astro student. What are the best practices for computer vision implementations? I think this is a very broad question. So,
well, this is a very open question, so it depends how you're going to implement it. So it's important to know how you are going to serve your model, how it's going to interact with users. Is it going to be a web app, or is it going to be on mobile device, or is it going to be on a tablet? Is it going to be real time or not real time? That's how you choose your model initially, actually. And so First of all, you need to identify how the model will be served, how the users are going to interact with that. That will tell you what constraints do you have, because for real time, you have obviously constraints on the time of your inference. It has to be fast. And for the medical applications like pneumonia detection, it doesn't have to be real time. You can have more relaxed constraints. So you need to also know your memory limits. For instance, if you want to use it on a mobile phone, you obviously have some memory constraints. If you can run inference on server with GPU is one story. If you run inference on the laptop with CPU is a second story. So you need to know all those limitations. Then you choose basically model and complexity of your model depending on that as well. And then also I will send you a link. You train your model, for instance, if you want more relaxed constraints, let's say medical applications have for diagnostics, let's say like pneumonia detection, or you want to do like web servers. So you train your model and then you convert your PyTorch model to TensorRT library through ONNX. I will send you a link how to do it. So basically, it's a lot of information about how to convert your trained model, your trained graph into that format. And then you can develop web servers, for instance, using Flask. Flask is very popular for developing those kind of things. And that's how your model will be solved, for instance. It's one of the examples. So obviously, that depends on the task. From task to task, it is varied. So this is maybe the simplest way to deliver your model to the user.
Thank you, Tanya. That's you explained it very well. So, so Revati says the guitar tuning analogy to neural network weights adjustment was very cool. Great presentation. Oh yeah, it was very nice. The analogy that you used. Actually, I think I'll always remember that now. So one question from Jack Martin is, which is your favorite paper from CVPR 2020 conference?
Well, I really liked my favorite paper when they had a 2D image and just it's from Facebook AR research when they had 2D image and it just went 3D. You know, you can see 3D model straight away generate from 2D images. I think it's cool, but I'm just reading it, so I can't comment more. I need to read more about it.
Okay, so what is your opinion about the future of computer vision? What kind of freelancing opportunities exist in CV? And please share your freelancing experience.
So basically, this is a hard question where everything is going. Indeed, because now we have all those networks kind of getting stabilized and we have all those frameworks. So you don't write those nets nowadays much. You just use ready versions and often you don't even need to train the model. You already have a lot of pre-trains and you can, for many tasks, you can just do inference. So this is all progressing this way that kind of to fit predict a bit, right? I see that there are a lot of, you need to look, I think, in a lot of unsolved problems that still require some attention. For instance, in the real time in tracking, you still use Kalman filters. Why? Because they're faster. So this is, I think, where it's going to progress, needs some progression. You need to look more into the video understanding and so on. So basically, see what is developing. What has been developed, it's getting stabilized pretty much, and it will be easier to do fit predict in future, obviously, because we're going to have more data, the data gets accumulated, we are going to have more pre-trained models, more ready solutions to use them out of the box. It's hard to say. I wish I could get that answer myself where everything is progressing in computer vision. It's hard to say nowadays. As for freelancing experience, you need to have a network. So for instance, all those options that I got were through LinkedIn connections and people that know me. So for instance, I would find a person who needs to implement some program on a plant, and I would do that little short project for him. I didn't use Upwork or anything like that. It's mainly came through networking. I think networking is the best for that because people know you or know something about you. So they're more trustful to collaborate with you, and it's easier in terms of communication. But you can also try to make a profile on Upwork and see how it goes. It will be hard in the beginning, I've heard, but then when you get some reputation and clients, it will be easier. But freelance is not easy. It's just, I considered it more like a supplementary experience, you know, not like for the full-time work, because it's not that easy to get a constant flow of projects and clients and so on. It's a lot of work by itself to find the work if you're freelancing. So I would think whether you want to go this way or leave it as a practice for a beginner, I don't know, for some period. Also, freelancing requires experience, so you have no advisor to ask things. You need to know how to make things straight away. So it means you can only take the tasks that you know well about. While if you go working in a company, you can deal with the problems that you don't know yet, but you can learn from your other coworkers. So you know some parts, but you may not know everything, and you still have a person to ask and to learn from, which is also important. So it's it's a difficult choice between
I think she's explained it very well, and it all boils down to the fact that you should also have a good network connection. You should make your work publicly available, maybe through LinkedIn, through Twitter, or organize or speak at meetups and give presentations. So there's another question. Have you used any libraries for explainability in deep neural networks, or maybe, I don't know, with context to computer vision?
No, I did not. I'll send you the link how you can visualize things, but no, I did not myself.
Okay. So yes, there's an interesting question. Can you mention a few Kaggle competitions for beginners to practice computer vision techniques?
So basically, nowadays you have melanoma classification, and basically I will start with classification problems, and I will choose the competition that has been already going on for a few weeks. So you have some kernels, some notebooks available, and I will start with some notebooks. So I'll just open Kaggle just a second. So Kaggle is really the best way to learn, as for me, Kaggle. That's how I started learning machine learning. So basically, let's see what they have. Competitions. So they have now quite a lot of computer vision, I think. So yeah, they have that melanoma classification. I think it will be the best to start because it has 2 months to go and it already has a lot of notebooks. So you go to the notebooks. Can I share the screen? I think I can. I'll share the screen. The entire screen, application window. So can you see it? Yeah. So you can go on Kaggle page and you choose competitions. So I think that melanoma classification will be the best to start with. You have also, because it has quite a time to go, like 2 months to go. For instance, if you have 10 days to go, it's not enough, definitely. you need some time to understand data and to try your models. And you click on that problem, and you can see here notebooks and discussion. So when you go to the notebooks, you can easily see, you can sort by the best score or the most voted, and you choose not the token. Something when you have a single model, for instance, you have here single model, inference, melanoma starter, and maybe somewhere training, PyTorch starter, efficient net. That probably will be the good one to start. And you look for the notebooks in PyTorch, and you understand them, and then you try to change things and train model by yourself, and that's how you learn.
Okay, so I think melanoma classification will be a good competition to start, and you should actually experiment with it. Next question is, can you share or point to some interesting resources in 3D computer vision? Any work in creating digital twin?
So basically, 3D computer vision is a big field. So for instance, you have LiDAR point clouds. So you have 3D reconstruction. I would go first to resource is a Papers with Code. There is a website called Papers with Code, and you choose the field computer vision, and you choose 3D, and then you choose your category of what do you want to do, like 3D reconstruction, working with LiDAR point clouds, 3D detection, and so on. And then you look into the papers, and also you can see the state of the art in that field. And you read that papers, and you see the code for them, and that will be the best resource, I think.
Okay. So we're having questions coming in, but we'll actually have to stop somewhere. So I'm just going to take the last question. So it's, have you experimented with Bayesian deep learning in computer vision?
Yes. What do you mean? It's like, once again, have I experimented with computer vision?
With Bayesian deep learning in computer vision.
With, can you type?
Yeah. I'll sure.
I just.
Okay, so till that.
No,
okay.
with Bayesian, no.
Okay, you're not. So if she gets some resources on it, she'll share with us, and maybe you can read it. So there's a question that I have a Jupyter notebook with model developed. How can I quickly convert it into a web application, which I can then serve?
So yeah, I will send again the links. So if you want to serve it, you need to look into the Flask, and so Flask services. And there is also easier way. I just forgot how to deploy models as a web applications. So I'll send the link here. Actually have it at hand. So this is a link, for instance. Deploy on Keras. Well, this is for Keras model, but it does not really matter. So everything will be the same as a web application. So in Python. So for instance, there is plenty of examples on the net. So you look on some example of already implemented web service. Usually it will be in Flask, and you go through that steps. You also need some hosting, so you can have your own host, or there are also some platforms available for that. I just need to find. I have my own hosting, so I can do my own on my own website. However, in internet, you can actually, I can't find it now. there is a hosting provider basically which is for free that you can use to make a web app for a model, but I cannot find it at the moment. So I need to send those links afterwards.
Yeah,
because
we'll
I
get
have
in
my
touch
own
with you.
hosting, but you have to pay for that. So
Okay.
because I bought it from my website, so it's not an issue for me. So you get this hosting, you get a Flask, you go through tutorials, and they give you step by step how to implement the model. I probably will send it to the YouTube channel.
Yeah.
Links how to make it.
So we have just the time for last two questions, and one question is which actually I had to ask her, but there's another one which I'll ask is what characteristics or what is a good laptop with what good configuration should be used for computer vision?
No laptop. It's better to be a server. You need a server. So I use a laptop, but I connect to the server.
Okay.
So I was lucky enough to have, there is a company, HostKey, in Amsterdam, who provides some quite well-priced servers, and they also give grants to researchers. Thanks to them, I made this pneumonia detection project. So basically, you can also have free credits from Google Cloud Platform. Sometimes Amazon has free credits, but it doesn't provide GPU access. So you need a server with GPU access, and you connect to the server, and that's where you do the training. If you want to get serious about it, you need to get a dev box. So you get a proper PC with GPUs like 2, 3, 4, and you work on them. And the laptop I only use to connect to the remote servers. You cannot really do deep learning. Well, you can,
So
but
if you're serious about getting into computer vision, you need to invest something.
Yes, it's
okay. So the last question is also a personal question, which I wanted to ask you. Why did you choose to shift from academia or maybe, so you have a PhD in physics. So how did this change to machine learning occur?
It's not really that big change, to be honest, because physics is not far from machine learning, in fact. So what we were doing in physics, a lot of regression and data processing, signal processing, also gradient descent algorithms. So those are part of physics as well that can be used in physics as well. It wasn't a particular machine learning field. However, all the techniques were pretty much the same. So, and what happened to me, I was in experimental physics working in the clean room. It's nanophotonics. You grow your semiconductor lasers. You dress up like doctors nowadays. You have a mask and gloves and all that protection because it's a clean room. So, and you want to avoid contamination. And the main sources of contamination are actually humans. So, and yeah, when I got pregnant, it turned out that I can't work there because it has a lot of chemistry. So pregnant women are not allowed to that room. And I realized at that time that, okay, I need to think how to fit my profession to something that women can do, like computer-based. So I started to do more theory, and that's when computer vision came up. And because I have PhD in optics, and optics is very well related to computer vision because you work with cameras. LiDARs are actually lasers. So you know how they all work, camera aberrations. You basically, experimental physics, you collect all those data using different cameras, different devices. And in computer vision, you need the data anyway. You often need to collect data as well for the specific task. That's when experimental optics comes in place, So I realized that this is kind of a complementary shift. So it's not entirely shifting career, but changing to something I can do from home, and it's okay with pregnancy. So during second pregnancy, I already was doing a research project with machine learning on my computer, and I could do it. So, but yeah, I think the main thing was when I got, a project, and I realized I cannot do that because it's a lot of chemistry, so I'm not allowed to do it. And that's I realized that maybe time to change for me.
Good that you changed. Good for us. And how did Kaggle happen?
Basically, it was just so popular. Everybody was talking about Kaggle, that you need to start on Kaggle. So I started my first competition just a week before the deadline. I thought it will be enough, So, and I think it was in Kaggle, there is a person with nick CMPM, who is very sharing of ideas. So he was in that competition, and he wrote how you can parallel submissions. It was like tracking path in Android Collider. Obviously, I chose physics because I thought, oh, it will be easy for me. So, and he wrote a lot of ideas. He shared. My mistake was that I've never read discussion till the last week. So please read discussions straight away. It has a lot of information. So I read his discussion. So I implemented algorithms. I got some position on the leaderboard, like around bronze zone. So I got quite hooked with that. So I only finished as number 60 on the bronze for the first competition, but I really liked it. And I realized that this is a great place to learn because people share the ideas and you can implement them. People share notebooks. In your life, if you just self-learner, like me on maternity leave, I was self-learner. It's important to have a support and to see those notebooks and to see those discussions as well. So it was very handy, because if you do something just by yourself, you don't have that much help. And plus you have a leaderboard, so you can see how well your program is doing compared to other participants. So it gives you some feedback how well you're doing. So I think it was just useful for me in this regard. However, Kaggle is far from real life, I must say that as well, because you already have all your data ready, usually even cleaned. You have your metrics already implemented. They tell you what the metric, your business case is already described and formulated in terms of machine learning. So it's not what's happening in life. So you need to gain understanding how to do that in life as well, because Kaggle is just some part. It can teach you some part, how to implement models, how to train models, but it will not teach you everything. So the best thing is to find a practice and to use Kaggle for training that particular area, but cannot teach you everything. So
yeah, I think very well put. So I think we've even gone into a little deep into everything. Thank you so much, Tanya, for taking out time amidst of such busy schedule, and your kids also, they must be waiting for you. Yeah. So thank you so much again. We've had a wonderful session, and I'm having such positive comments from everybody. We'll share the links with all of you, and even if you have any queries, you can ask, and I'll in turn ask Tanya, and we might get her back onto our channel maybe in future, because it was a session worth attending. So thank you so much, everybody.
Thank you.